The second presentation on how to measure frequency response functions, we will spend on how we can excite the test object. What alternatives do we have, and what pros and cons do they have? We will also talk about how to measure excitation, how to measure the response, and also what kind of data acquisition system we need. So let's start now with the very, very important subject of excitation. How to excite the test object. So, as we know from a previous presentation, we have to measure the accelerance function, frequency response function, between an excitation and an acceleration. And we need to do this in a specific frequency range. So, the definition, the definition used for the measurement that we use is the following. The frequency response function is the ratio of the spectra of the response over the excitation. So the first important requirement we have is that the excitation must contain high enough energy in the frequency range so that we can measure it. If it's too low so that we can't measure it, then the quality of the measured frequency response function will be poor. So this is a must. Measurable energy in the frequency range for the excitation. And the same goes, of course, for the response. So that means that in principle, then, that the excitation must be large enough to excite a measurable response in the frequency range that we are interested in. So these are two basic requirements that we need to fulfill with our excitation. And typically there are of course many techniques to excite a structure, but there are two standard techniques. And the first is an impact hammer. In principle, we have a hammer here with a force transducer mounted in the tip. So we hit with this on the excitation point here. And then, of course, we measure the response with an accelerometer in this point. And the purpose of this impact hammer is actually to simulate a Dirac delta function. Because a Dirac delta function, as you know, has a frequency spectrum equal to 1 for all frequencies. In practice, of course, a Dirac delta function is not possible to achieve, but we try to achieve a good enough impact pulse, so that we have almost constant frequency spectrum up to a certain frequency limit, a certain upper frequency limit. That is, of course, the highest frequency range, frequency that we want to measure. And the upper frequency limit, this F up, is we can actually control this with the hammer tip material. So if we choose a hard tip, for instance, a steel tip, then we achieve a very short impact pulse, a short pulse time. And that will create a force spectrum with a wide frequency range like this. If we instead go for a soft tip, we can get a long pulse time, and the typical material here is rubber. And then, of course, as you see here, the pulse time will be long, and from Fourier analysis we then know that the force frequency range will be much more narrow. So it will extend from 0 to a much lower upper frequency limit than in the first case. So a rubber tip would be preferable if we are only interested in a fairly low frequency range. Then it's waste of time to go for a wider frequency range as we can get with a steel tip. Another advantage then with the impact hammer, is that the influence on the test object is minimal, because the hammer is in contact with the test object only for a very, very short time, the impact time. And that's something that is worth to strive for. It's also very simple to use, and that means that it's quick to measure with. We get quick measurements. So, to conclude, I would say that this impact hammer is the first choice. If it's possible to get good measurements with the impact hammer, then you should choose it. The second standard technique is to use an electrodynamic shaker. So in principle, this is, well, it's like a loudspeaker. So you have a coil and a magnetic part in here that is connected to the shaker table here. And that is, the shaker table here is connected to the force transducer via this stinger, the push rod, the stinger, as it's called. So when you run alternating current through the coil, then the electromagnetic forces this shaker table to move, to vibrate in in the same way as the alternating current changes with time. So this means that you can achieve a very, very flexible frequency range, because if you can actually design the current you'll feed the coil with to contain the frequencies that you want to measure. If you, for instance, choose a perfectly sinusoidal current, then of course, if the system now here is linear, then you will get a sinusoidal excitation force. So you will sort of concentrate all excitation energy to one single frequency. Now that could be very useful in some cases, in some problematic measurement cases. If you use, in the other hand, if you use a white noise coil current, then if you have a linear system, then of course the excitation force will be white noise character. And that means that since white noise contains all frequencies in equal amount, you will get a constant frequency spectrum for the excitation. And that can be good. You can also adapt select the coil current so that you have a flexible excitation strength. And that means that you can sort of put more excitation energy into the system at certain frequency ranges and lower at other frequency ranges. If, for instance, the test object is very sensitive to excitation in this frequency range, you can and it's insensitive in these two ranges, then you can supply more energy in these insensitive ranges than in this sensitive range. So you can design your excitation spectrum in a very convenient way if you use electrodynamic shakers, and that's a very, very strong advantage. A disadvantage is that you have some influence on the test object, because the force transducer here is actually mounted to the test object, and it's rigidly mounted. So you will always have dynamic force, interaction force here between the excitation system and the test object. The purpose of this stinger, the push rod, is to minimize this, make this influence smaller, but it's impossible to avoid this influence. It's also quite complicated to use, ranging gluing, mounting the force transducer, suspending the shaker, the push rod and everything, it's time consuming. Also, of course, to design the coil current so that you achieve the frequency spectrum you need, it also takes time. So all this makes the electrodynamic the second choice to the impact hammer. So if it turns out that the impact hammer is impossible to use because you get poor measurement data, then you can go for the electrodynamic shaker and try with that. This shows shaker mounted in suspended in strings here to avoid too much influence from the environment, and here you can see the push rod, and here is the force transducer, and it's actually a tire measurement we are doing here. And if we go now to the response measurement, the response is, of course, if you are interested in vibration measurement, it's accelerometers that is used. And in this case, as you can see, we have 5 accelerometers mounted here. And what you should look for, what is critical when you choose type of accelerometers, is first of all the sensitivity. It must, the accelerometers must be able to pick up the small vibration amplitudes, the small vibration signals in the mounting points, and that means that they have to be sensitive enough. You should also be able to pick up the acceleration in the frequency range that you need. So if you have a very, very wide frequency range, high frequencies for instance, then that might decide which accelerometers to use. The mass is also an important factor when you choose accelerometer. In this case, when you mount these accelerometers here on a rubber surface, this tire, they cannot be too heavy. The mass cannot be too high, because then you will have a loading influence from the accelerometers on the test object, and that's not good. So the accelerometers must be lightweight. The mass must be small enough, so small that they do not influence the measurement object, the test object. So why do we need more than one accelerometer then? Well, the answer to this is, of course, that if we can use a simultaneous multi-channel measurement system, then we can measure, in this case, 5 frequency response functions simultaneously, and that speeds up the measurements, of course. I talked about data acquisition. We need a system to acquire the data, the measured signals. And what kind of data acquisition do we need? Well, first of all, we need some preamplifiers, and that is, of course, because in many cases we need to amplify, make the transducer output signals stronger before they are picked up by the data acquisition system. The data acquisition, that is usually, in frequency response function measurement, it's always 2 channels or more. 4 and 8 channels is a common choice. And that means that we can measure 4 or 8 or more frequency response functions at the same time. The data acquisition system must have low-pass filters. A low-pass filter is used as an anti-aliasing filter, and we will come back to what this is in a later presentation. But this is a serious error that is introduced by the analog to digital conversion process. And to reduce this error, we need anti-aliasing filters. It's also a must that we have synchronized analog to digital conversion. Synchronized here means that the sampling of data must be synchronized between the channels. If they are not, we will achieve phase error in the frequency response function we measure. We must also have high enough sampling frequency. The sampling frequency sets the upper limit of the possible frequencies range that we want to measure. As a rule of thumb, well, in theory, if we want to measure up to a certain upper frequency limit, then we must sample at least twice with at least twice as high sampling frequency. So if we want to measure up to 1 kilohertz, then we need to sample at least 2 kilohertz. In order to be on the safe side and avoid errors, a common choice is to sample with the factor 2.5 times the upper frequency limit. And the reason for this is that the filters, the anti-aliasing filters we use, is not ideal. They have some slope. They have a specific slope then that makes this choice a safe choice. Finally, but not least important, we need an A to D, an analog to digital conversion that uses a sufficiently high dynamic range. And that means that for modern measurement systems, we use A to D converters with typically 24 bits. And this means in practice that we have a dynamic range, an amplitude range for the signal ranging from 0 up to 2 to the power of 24 levels, discrete levels. Okay, so when we have acquired our measurement data, that means that we have, with our data acquisition system, we have digitized and sampled the excitation and response sequences. So we have digitized and sampled acceleration and force signals. Digitized and sampled means that we have vectors with a finite set of signal data. And the question then is, how shall we process these signals in order to get as good frequency response function as possible? And that is the topic of a following presentation.